Welcome all of you. In the last 3 classes, we have been extensively discussing NOE phenomena. In the last class especially, we discussed about correlation time, how they are related to spectral density function, and how it affects NOE. And we discussed a lot about spectral density function, where what happens when j omega r omega tau c is very much smaller than 1, extreme narrowing condition, and omega tau c is very much greater than 1 is a diffusion limit. And also we also saw that omega tau c is approximately equal to 1, it is a condition, it is a situation where there won't be any NOE. We saw the plots of various plots of omega tau c was a function of signal intensity enhancement NOE, and we saw it is positive for small molecules, negative for bigger molecules. That is what we saw. And maximum gain in the signal intensity in an extreme narrowing condition, we got the parameters equations for transition probabilities W1, W0 and W2, substituted that in the Solomon equations. Then we saw that in the extreme narrowing condition, the gain in the intensity or NOE is half. Of course, depends upon the ratio of the gammas. For homonuclear case, it was 0.5. That is what we observed. We saw that. And for different heteronuclear case, gamma factor comes into picture. And I showed the example of varieties of nuclei where gamma NOE enhancement factor was there, and it can start from for carbon 13 200% to varieties of nuclei up to even 1600 times. We saw that. That means if I record the carbon 13 spectrum with proton decoupling, then I am going to get twice the enhancement of the intensity, 200 times, 200%, not 200 times, 200%. Similarly, we also saw that if I decouple carbon 13 and absorb proton, enhancement will be of the order of 12.5%. That is what we saw. So, all these things we understood. Of course, NOE is understanding concept is a bit difficult. Lot more things are there to discuss. As I told you, there are exclusively 2 books only on NOE itself. Imagine the vastness of the subject. So, everything can't be discussed, but I gave you the basic ideas, concepts, everything to understand. And when you do an NOE experiment, there are number of NOE experiments which I discuss in this class and the next class, and then we will understand how to do the experiment, everything. But there will be some complications by doing NOE. Those complications we have to understand before interpreting the NOE properly. So, we will start with that today. So, starting with the complications of NOE here. Selective saturation of resonance is a very, very important. I am talking about steady state NOE, because I tell you what is steady state NOE, everything. So far we have not introduced 2D NOE. That is why NOE means, as I have been telling you, I hit a particular resonance and see the change in the intensity of the other peak. So, how do you do this selectively hit this one? Selectively I have to saturate one of the particular resonance. The selectivity of the thing is very, very important. The frequency has to be properly set. Otherwise, then little disturbance, and if you saturate a neighboring proton, then because of the spillover of the RF, that can cause problems. So, that means the selectivity of the frequency is an important condition. And of course, if you have a multiplicity at the peak, where do you want to hit it? You have to perturb exactly at the center of this and make sure that multipliers are subjected to perturbation properly. If all the multipliers are not equally perturbed, are not equally saturated at a time, then that results in selective population transfer. We discussed this long back. That can also cause problems. Antiphase terms of the J coupled multipliers are going to be seen. That is what we observed in population transfer experiments when we discussed that. So, integrate, if you take the positive negative intensity signal antiphase, if you take the area of that integral area, that is 0. So, that means if you do not selectively exit, if you do not exert the multiplicity or saturate the multiplets of the peak properly, if they are not perturbed properly, unequal perturbation can give rise to antiphase multiplets, and if you take the A total area, intensity of that area of that particular multiplied becomes 0. So, it will mask the genuine NOE. There may be NOE because is of unequal perturbation, whatever NOE is there will not be seen, it gets masked. So, that is another thing. Selectivity and uniform perturbation in the multiple rates are important things. This is an example to show what happens in a spectrum like this. This is selectively saturated, but you see it is not uniformly saturated, it so happens. And if when the difference is taken, see there is a antiphase components there. Now, if you take the area of this, what will happen? It may become 0. Then you will not see NOE if at all, if there is any. So, these are all problems of unequal perturbation of multiplates. The multiplates are not properly perturbed, you are going to get this type of problems. There is another effect called 3-spin effect. We have to discuss that. For example, I have 3 spins. So far, all understanding NOE everything with two spins we took into account. Understanding omega tau c and dipolar relaxation, everything we took only 2 spins. It can so happen there can be many spins neighboring. For example, 3 spin. There is a famous thing what is called 3-spin effect. I am irradiating proton S, let us say, or S, whatever it is, and it is giving NOE because of cross correlation with I spin. But there can be a leakage of this I spin. Instead of gaining magnetization, it may lose it by giving it another spin next to it. This is called a leakage. This is a 3-spin effect. It can cause problems. For example, I will tell you how there could be indirect effects. Lot of indirect effects could be there. Take for example a molecule which are linearly is like this. There are linear molecule in a realistic molecule. I am saturating proton A. Assuming there is an NOE, I must see the intensity increase in B. That is true. If there is NOE, I will see that. And there will be dipolar cross relaxation between B and C. As a consequence, there is a intensity decrease here on C, and also it can so happen this also can decrease because it is giving its magnetization to C. It can happen. So, this is all indirect NOE effect. If the third spin is there, instead of seeing the intensity may come down, or here also it may change, intensity may change because population is getting transferred from B to C also due to dipolar cross relaxation between B and C. These are all the important factors that one should know. And this is called a spin diffusion. The spin diffusion means there are 3 like this. You are saturating A, B should have enhancement, B can give it to C. But this is a spin diffusion phenomena. That is a linear molecule. Take a situation of a angular molecule which has some angle like this. A, B, C are not linear. It is an angular structure is there. For the angular structure like this, there can be direct NOE between A and C. In the previous case, it is indirect NOE because A you are saturating, your B getting enhanced, B will give it to C, and it is you see NOE intensity and C, it is not actually real because of the indirect effect from A to B, B to C. Here, I mean angular molecule with an angular structure, I am irradiating A, let us say. A direct NOE effect can be there between A and C. That is positive. But what will happen? Because this can get nullified due to indirect effect between A and C. What will happen? So A to B, B to C will be there. There can be direct NOE between A and C, that is positive, we should expect. But because then when you are saturating this also gets saturated, and then this gives this thing to this. Suppose then it can sometimes so happen, or this can give back to its magnetization to that. It can get diminished or get even nullified because of indirect effect between A and C. Although there is a direct NOE, this can get suppressed. Okay. These are some of the problems: 3-spin effect, angular molecule, linear molecule, varieties of things we know that, and frequency of selectivity, equal perturbation of the multipliers, all are needed. So many complications are there in NOE. I just wanted to brief you, there could be many complications in NOE when you are doing the experiment. All right. Now, how many types of NOE experiment we can do? There are different NOE experiments possible based on how the experiments are designed. For example, there can be what is called a steady state NOE. That is a only difference NOE conventionally what we used to do earlier. Of course, now also we do. There is another called transient NOE, 2D NOE. There is also gradient NOE, steady state NOE, where that transient NOE we use in the 1D format with gradients. That's also there. Usually 2D NOE is transient NOE, 2D NOC. Rotating frame NOE called ROC. There is also called transferred NOE, TRNOE. Heteronuclear overhauser effect, OC. Couple of them only I have listed. All this, there are different types of NOE experiments. All are homonuclear and this is heteronuclear. We will see quickly couple of them, how it works. I mean, idea basically so far we have discussed, conceptual understanding of NOE remains same, NOE. There is not much of a difference, but small experimental modifications will be there. And what will happen when in each of these experiments? Quickly we will see a couple of examples. What is a steady state NOE? This is very simple experiment where we are going to selectively saturate one of the spins for a long time with a very low power, and then apply 90-degree pulse, start collecting the signal. During the long pre-saturation time, what happens? Spins are coupled via NOE are able to reach a steady state. They are coupled to each other. I know you are saturating a spin, it may give energy to I spin. Slowly it will NOE will be built up on I spin, and then it will reach a steady state. It will reach equilibrium. This occurs on the T1 scale and the relaxation time scale. So this is the simple example, that is why it is called a steady state. Saturate one of the spins and NOE coupled spins coupled via NOE after a long time reach a steady state. That is what it is. Then how do you carry out this 1D difference NOE experiment? Very easy. All that you have to do is, you have to selectively saturate a proton or a particular spin or signal by a very low power RF. I showed in the previous slide pulse sequence. Very low RF, pre-saturated, apply a 90% and collect the signal. That is what we do. That is a simple one-dimensional experiment. Only thing is pre-saturation is done before applying a detective pulse, that detection pulse 90-degree to pre-saturate the selected signal. Okay. Apply a similar RF power at a very far off distance so that none of the intensity of the signal are disturbed. They should not be perturbed. Why? We have to maintain the ideal conditions so that I want to see the difference of the two. What we do is, first collect the spectrum by saturating a proton, and then identical similar RF power you have to apply far away from the spectrum of your interest, RF, and then far away. So that means if there is a disturbance because of the RF, it is uniform throughout for both the spectra. Collect the spectrum. This one which is you are not saturating any signal, you are saturating at a far off place, is called a reference spectrum. Take this reference spectrum and then take a difference of this spectrum, reference spectrum with the spectrum you have chosen or you have collected after selectively saturating a particular signal. Take the difference like this. This is an experiment. Do a control experiment where you can irradiate the signal at very much far away, that is called off resonance, collect the signal. Do on resonance and selectively on a particular signal, continuously pre-saturating both, identical power in both the cases, again collect the signal, subtract, take the difference between the two, and then you are going to see NOE. If there is any difference, if there is any enhancement of the signal, if there is no enhancement on anything, if you take the difference, the identical spectrum will be there, then there won't be any signal, you will get 0. But if there is NOE on particular some of the signal, when you are selectively saturating one of the signals, then that signal will show intensity, that will not get nullified when you take the difference. This is what happens. The difference of the two spectrum shows NOE enhancement if there is any. Okay. This is an example to show. See, we are saturating one of them. This is a conventional spectrum and this is what is saturated, and then you see the difference. This is this is a normal spectrum. This is spectrum saturated, this peak is saturated here. You see the difference? I will tell again, this is a normal spectrum and this particular peak is saturated here. There is no signal because of saturation, and the difference of this and this is taken. Of course, this is negative because it is saturated, and this is full signal is here and there is no signal here, that is saturated. And you see this is there is enhancement here and here. All these things get completely cancel out, whereas there is enhancement here and here. That tells you this proton and this proton are having NOE, are getting NOE because of this proton you are saturating. That will establish these two are in space close to each other. There is spatial proximity between these two. That is what it tells you. Okay. If the saturation recovery is not set to few T1, we have to set for a few T1. Selective saturation is not enough to create full NOE. Of the order of several T1 you have to put. Normally, what we have to do is 5 times T1. 5 times T1 is, otherwise spins would not have completely relaxed back. Saturation signal would not have completely attained equilibrium. Only after it attains equilibrium you have to apply a pre-saturation pulse. Otherwise, there will be error in the NOE. So, you have to wait for certain time. Normally 5 times T1 you have to do, but in most of the cases in the routine experiment that is not necessary. We will give only 1 or 2 times T1 or maximum 3 times T1 and then do the NOE experiment. That is a steady state NOE. After conceptual understanding of all these techniques, we will take several examples of 1D NOE, steady state NOE, everything, and then interpret the spectrum really with many examples. Now, I will introduce a HOSI. HOSI is called Heteronuclear Overall Spectroscopy. Here, pulse sequence is very simple. You have 90 tau 90, and then we have 180 pulse at the center of one of them. Obviously, that causes decoupling. This is what happens. Here, the magnetization evolves during the T1 period. I am applying 90 pulse. So, all the at the proton frequencies magnetization is evolving, and then we apply a 180 pulse here, that causes decoupling between two spins, and then apply a 90-degree pulse again on the proton channel, and then mixing time here, mixing pulse, give a time for the mixing. Spins will start mixing, talking to each other. After some time, apply a pulse on the detection channel, that is X. You are detecting X nuclei while decoupling proton completely. If it is carbon 13 you are doing, this is carbon 13, this is proton. Apply a proton pulse, things evolve here at the proton frequencies and decouple carbon proton coupling here, and then in the T1 dimension apply 90-degree pulse, allow the spins to mix. There is exchange of energy between the spins based on the spatial proximity between two heteronuclear spins. Then apply carbon 13 90-degree pulse, collect the FID while doing proton decoupling. This is a simple pulse sequence for HOSI. All right. This is an experiment to show how we can do a HOSI on varieties of nuclei. This is a HOSI spectrum of proton and lithium. See, this is the thing here, this is the proton here, and lithium is giving correlation to this, this and this, and not to other things. Based on the correlation, you will know that's how close they are in space. This is what it is, and this is a classic example from our work. This is a molecule which we were looking at. Here there is CF3, there is CF3 here, and this is HOSI. Here there is fluorine and proton. Our idea was to find out whether there is any, how close they are, because we were working on the hydrogen bonding. We want to see the spatial proximity is important for hydrogen bonding. We wanted to see how close they are in space. So we did fluorine 19 HOC, heteronuclear overhauser effect. In which case, if there is a there is a spatial proximity between these two, we must get the cross peaks. That's what we observed. We did that, and we are going to see cross peaks here. We observed that. Okay, this is proton axis. This is fluorine axis. There are two fluorines here. Each of them having some giving rise to certain cross peaks. This is the next one. To compare that, we also did the HOC. Of course, we have not discussed about the 2D NOC. I will discuss that when I come to a detailed discussion of NOC. A lot of examples we have to take. We will discuss that. This is 19F NOC here. That establishes spatial proximity between this CF3 and this CF3, and that's what it is. And this is CF3. This is a diagonal peak, gives the chemical shift, and this is a cross peak, and this is a cross peak, showing they are close in space. These are all NOE cross peaks. Here, of course, is the HOC. This cannot be symmetric like this, because heteronuclear, I told you, like in HSQC, they are not symmetric like in COSI. Similarly, here NOC is symmetric, but not HSQC, not HOC. Another one I want to introduce is what is called a ROC, rotating frame overhauser effect. Why do we do that? What is meant by rotating frame? See, a lot about rotating frame, everything we discussed, I have discussed in one of my very first or second courses. If anybody is interested, they can see some of the lectures there, where I discuss what is rotating frame and everything. Now, look at this graph. We saw this graph, I told you. This is a situation where omega tau c is equal to approximately 1, where you will not see any NOE. This happens for small and mid-sized molecule. Now, I want to analyze this spec, use the NOE for various purposes. NOE can be used to establish some assignment, some region specificity of the molecules, finding out spatial proximity, conformation, etc. But then if NOE is not there, how can I use it? This is a problem now. At omega tau c equal to 0, there is no NOE. How do you overcome this situation? Of course, one thing is change the spectrometer frequency, because it depends upon omega tau c. Change the spectrometer frequency. Instead of 100 megahertz, go to 800 megahertz or whatever the frequency. Or change tau c. Tau c changes means molecular tumbling. How do you change the molecular tumbling? You vary the temperature, increase the temperature, tumbling becomes faster. If it is fast, lower it, tumbling becomes slow. Or change the solvent of different viscosity. If the viscosity is very, very small, molecules tumble faster. In a highly viscous solvent, they tumble slowly. So, various experimental tricks we can adapt. If you want to overcome this omega tau c situation, which is equal to 1, where there is no NOE situation, you can do any of these three things. Change the spectrometer frequency, change the rate of molecular tumbling by changing temperature of the solvent. All right. Instead of altering the solution condition, why can't we do a different experiment? That is, instead of physically altering all these conditions, we can do that. Then we can do NOE in the rotating frame. That is an advantage. In that situation, what is the advantage, you may ask me? Why should I do in the rotating frame? Remember, in the rotating frame, there is no negative NOE, no zero NOE, always positive NOE you will get for any size of the molecule. So, why can't we do that? So, that is what we do, but only thing is, it has a limitation, is less effective for molecules longer T1 due to application of longer mixing time here. We are in the rotating frame, we are going to apply a longer mixing time. As a consequence, then if your spins have longer T1, then what will happen? It will be less effective. Don't worry about that. That's some condition, some limitation which I told you to be careful while doing the experiment. Let us see about the cross relaxation rate for homonuclear spins during NOE and doing ROE both. This is what we observed. NOE fact. This is cross correlation time, cross relaxation time, not gain the signal intensity. Don't confuse with rho I. Yes, that is not that. This is sigma IS, cross relaxation. This is the cross relaxation term for NOE. The same cross relaxation time you can calculate for ROE this turns out to be this. Now consider a situation, varieties of situation here. I want to take the example here. Supposing omega tau c is very small, or omega tau c, consider a situation omega tau c is approximately equal to 1. In a situation omega tau c equal to 1, then what will happen? See, this is 2, then still it is a positive term. I am sorry, not that here. Now I am this what I wanted to show you, this one omega tau c, still it is a positive term. Here of course things different, I am not discussing that, varieties of things will happen. In the ROE, when omega tau is approximately equal to 1, then you will see that 3/2 plus 2 into this one, this cross relaxation is there, that is always there, that gives rise to positive NOE. The ROE is always positive for all values of omega tau c here, because cross relaxation is there. For small molecules, ROA matches with that of the NOE. Approximately 40% matching is there, NOE approximately 40%. For our large molecules, ROA goes up to 68%. For small molecule, there is no issue. It can match with their transient type of NOE. This is a steady state NOE we were talking. ROA we can also do in the 1D way and 2D way. I will tell all those things later. For a small molecule, ROE matches with that of the transient NOE, what you get up to 40%. For large molecule, this goes up by 68%. Under no circumstances, ROE becomes 0. Under no circumstances. NOE can become 0 when omega tau is approximately equal to 1, but ROE never becomes 0. That is the important thing you should remember. So, the NOE and ROE growth rates are identical for small molecules. If I look at the growth rate, how the NOE is building up, in both the situations it is identical, but for large molecules they differ a lot. That is what we see. Growth rate is up to 68% for large molecules. All right, we will see this one. Consider a situation omega tau is very much smaller than 1. The cross relaxation rate for both transient and this thing, transient NOE, that is NOE and ROE, can be given like this. For omega tau is greater than 1, this is what it is. For for in the situation omega tau is smaller than 1, this equation applies to both NOE and ROE. When omega tau is larger than 1, this and this are different. ROE is different. NOE. See here, ROE and NOE both are different. One has negative sign, other is positive. So, dependence of ROE and NOE on omega tau c for an isolated 2 homonuclear spins, if I consider, this is how it is. ROE starts here, goes here from 40% up to 68%, always positive. Whereas NOE starts with 50%, comes down, it goes to 0 and goes negative. This is a simple graphically illustrates and omega tau c how the ROE and NOE will change. As omega tau c keeps increasing or changing here, as on the logarithmic scale, ROE keeps building up, whereas NOE from positive becomes negative. All the time you should see here, ROE has never become negative, starting with positive and goes only at positive. For large molecule, ROE grows twice as fast as NOE, and as an opposite side here you see. ROE develops conceptually in the magnetization the transverse plane, whereas NOE is developed along z axis. This is a very interesting thing. Of course, when we discussed about the NOE, I told you magnetization transfer takes place only along z axis, whereas NOE whereas ROE, it will take place in the xy plane, transverse plane. Remember two things, NOE development is there along z axis, along the longitudinal axis, whereas ROE development is along transverse plane in the x axis or y axis. So, magnetization exchange during NOE and ROE, if you want to see pictorially, it is like this. In the ROE, they have antiphase magnetization vectors, one for the inverted spin and the other one which is closed in space. where the magnetization transfer takes place. This is the inverted spin, this is the other spin. And in the ROE, same thing happens. This is the inverted spin and the other spin is here. Both are antiphase in the y axis, along y axis in the transverse plane. The effect of spin lock is to retain the spins. We are going to, I will show you in the next one, the pulse sequence of that. There is spin lock pulse in ROE. The effect of spin lock is to retain the spin vector so that it won't get disposed of. So that ROE develops only during this time due to cross relaxation. If you don't spin lock it, then the vectors may start moving away. So, this is a simple pulse sequence for 1D rosy pulse sequence. We apply 180 pulse on the selective spin, followed by immediately a 90 pulse, apply a spin lock, this is called a mixing time, that is where ROE takes place, collect the signal, that is what it is. ROE develops during mixing time. This is a simple one dimensional rosy pulse sequence, ROE. And this is what is called the rotating frame. When you are doing the spin locking, your spins are in the rotating frame, and that is where ROE is going to develop. Okay. So, for ROE, the targeted peak is always first inverted by a selective 180 pulse and then followed by a non-selective pulse. Then what will happen? The effect is a 270 pulse. When you have a 270 pulse, the signal gets inverted related to other peak. It is negative intensity, because you have a receiver here and bring the magnetization along this axis. This is positive. The signal is on the other direction. After bringing it by 270 degree, it is a negative signal. So, there is a negative signal will be there. So, this magnetization is spin locked in the transverse plane. What happens during spin lock? Of course, chemical shifts are refocused. Okay, that is what we discussed in the toxi. When we discuss toxi, during the spin lock, spins lose their identity. There won't be any chemical shift at all. They are all refocused, and spins will relax only in the rotating frame. That relaxation time in the rotating frame is called T1 rho. Spins relax in the rotating frame. Still, even though they are spin locked along the particular axis in the transverse plane, spins can still relax. That is called relaxation in the rotating frame, denoted as T1 rho. Okay. So, in NOE, the effective field is B naught, but in ROE, the effective field is B1. Why? I showed you in the graph. NOE, this is both source, inverted source is along z axis, negative z, and other spin is along z axis. But in the ROE, it is like this. One is x axis, y axis, other is minus y axis. That is the rotating frame. In the rotating frame, the magnetic field is B1, RF field which you apply. Whereas in NOE, the magnetic field is static magnetic field, which is huge, very large. This is what makes the NOE dynamics completely different in both the cases, because magnetic fields are different. Let us understand what it does. If you take gamma B naught in the resonating frequency, it is in megahertz. If the B naught is huge, of the order of several Tesla, whereas gamma B1 is very small, of the order of few kilohertz, because B1 is small. So, gamma B1 is very much smaller than gamma B naught. Similarly, omega 1 is very much smaller than omega naught, because they are all related to each other. Omega is equal to gamma B naught over 2 pi is the resonating frequency. That is what we discussed. Thus, for omega tau c is smaller than 1, for all values of tau c, you have everything is positive. Omega tau c for smaller than 1. Molecules behave as if they are in the extreme narrowing limits. Hence, ROE is always positive. It is like a small magnetic field. It is in extreme narrowing limit. Hence, ROE is always positive. And of course, we can extend this to a 2D way to do the experiment, everything. I will come to that. Okay, I may not go to 2D, but same experiment if you do in here, you vary this as a function of T1 and collect the signal and apply spin lock for the mixing. This only you vary, collect signal here, this is T2, and then do the 2D Fourier transformation, you get a signal like this. Okay, this I will come to that later, and there are also certain complications in rosy everything. Since the time is getting up, I am going to stop here. Today what we discussed is about lot of things about the NOE, NOE experiments, starting from varieties of things we discussed. like several experiments. What is ROSI, steady state NOE, what is HOSI, how we get the signal, what are the pulse sequences in HOSI, what is the pulse sequence in ROSI, and what happens to ROSI in the spin lock sequence. In the omega tau is approximately equal to 1, there is no NOE. In such a situation, instead of changing the physical parameters, we can go to an experiment called ROSI, where you can do the NOE in the rotating frame. In that case, NOE is always positive, never goes to negative, never goes to 0. That is what we saw. And we saw that for small molecule, NOE is up to 40% matches with the ROE matches with NOE. For bigger molecule, it goes up to 68% and always positive compared to NOE, which is the opposite in sign. And the growth rate is faster at for ROE for bigger molecules. It goes up to twice the speed. So NOE growth is, we observed all those things, how the thing NOE grows in both NOE, ROE, everything. Our signal grows, signal gain will be there in both NOE, ROE, etc. We discussed a lot today. So we are going to stop here. Bit more about complications for ROE, etc. I will tell in the next class. We are almost coming to the end of the understanding of the concepts of NOE. I took almost 2 to 3 classes or even more, maybe 3 classes, just to tell you about NOE and its concept, because it is a huge topic to understand. Lot of complications are there, but it gives a very beautiful information about the structure of the molecules. So there are a number of experiments, I said, in NOE itself we can do. I mentioned only a couple of them and gave 1 or 2 examples, but we will see the utility of them in the subsequent classes, 1 or 2 of them. So I am going to stop here. Thank you very much.